I want to tell you about something that distracted me for years. And if you're honest, it probably bothers you too. Is quantum probability real, or is it just a confession of ignorance? Because most people think randomness is what you get when you don't know enough, like flipping a coin in the dark. And honestly, I used to think that too. I kept wanting there to be something underneath, some hidden clockwork that decides where the electron lands, and we just haven't found it yet. But then I ran into the same problem again and again, in the double-slit experiment, in radioactive decay, in light itself, and each time, nature refused to behave like a machine with secret gears. And somewhere along the way, I discovered something that changed how I think about chance forever. Quantum mechanics doesn't merely use probability, it seems to be built out of it. So let's take a walk together, and I'll show you where my intuition failed me, and why that failure is the most beautiful thing about physics. When I was a young man learning physics, I was raised, like almost everyone, on the idea that the world is basically a well-behaved machine. You push something, it moves. You know where it is, you know where it's going. Even if the machine is complicated, like the weather, you still feel, deep down, that it's determined. Now, of course, we already had probability in physics before quantum mechanics. We had it in thermodynamics. We had it in statistical mechanics. But in those cases, probability is sort of a practical trick. You've got too many molecules, you don't know every position and velocity, so you average. You say, well, I can't predict the exact molecule that hits the wall, but I can predict the pressure. And nobody loses sleep over it, because you feel the randomness is in you, in your ignorance, not in the molecules. Then quantum mechanics comes along and says, no, no. Even if you know everything that can be known, the best you can predict is a probability. And that's when trouble starts, because that statement pokes directly at the kind of faith people secretly have that reality is a definite thing, doing definite things, whether or not we look. I remember teaching students and watching their faces tighten up right around the same moment. They'll be fine with equations, fine with math, and then you say, the electron hits here with a certain probability. And they go, yes, but where was it really? And I have to tell them the terrible truth. That question might not have an answer in the way they mean it. I'm not trying to be mystical. I don't like mysticism. I like finding out. I like experiments. I like to know what nature does. And one of my favorite rules, maybe the only rule that really matters, is don't fool yourself. Because you're the easiest person to fool. So I tried not to fool myself about what quantum mechanics was saying. And for a while, I did what many physicists do. I learned how to calculate, and I tried not to ask the questions that made my stomach hurt. But there's a difference between avoiding a question and answering it. And the question kept coming back. If quantum mechanics only gives probabilities, are those probabilities describing something real in the world? Or are they just a temporary language until we find the deeper, deterministic story? Around this subject, there's a famous line I've said in lectures, half joking, half deadly serious. I think I can safely say that nobody understands quantum mechanics. People repeat that line like it's a surrender. But I didn't mean it as surrender. I meant don't confuse being able to calculate with having a picture in your head that's truly faithful to nature. Because your picture will try to become classical again. It'll try to smuggle in hidden gears. And quantum mechanics punishes you every time you try. It wasn't philosophy that convinced me. It wasn't someone's interpretation. It was something much more brutal. A single experiment that keeps humiliating any classical story you invent. The double-slit experiment. In my lectures, I said something about it that I still believe is true. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. And what I want to do with you is not just repeat the mystery like a bedtime story. I want to relive the way it attacked my instincts, until I had to admit, maybe probability isn't a fog covering reality. Maybe probability is one of reality's fundamental rules. Imagine I've got a little gun that shoots electrons one at a time, so slowly that there's never more than one electron in the apparatus. There's a barrier with 2 slits, and behind it a screen that records where each electron lands. Now, you might be thinking the same thing I thought. If it's 1 electron at a time, each electron goes through 1 slit or the other like a little bullet. So I say, fine, let's do the experiment. If it were bullets, then with both slits open, the pattern on the screen should be the sum of the 2 1-slit patterns. Just add them. Common sense. But when you actually do it with electrons, you get interference fringes. Bright bands where lots of electrons arrive, dark bands where almost none arrive. As if each electron is a wave going through both slits, interfering with itself. Now here comes the humiliating part. You don't get the interference only when you shoot a lot of electrons at once. You still get it when you shoot them one by one. At first, you see random dots on the screen. 1 dot here, 1 dot there. It looks like chance, like noise. But keep going long enough, and the dots build up into a clean interference pattern. It means that whatever determines where the electron lands is not the kind of hidden randomness you get from ignorance about initial conditions, because we're not missing the conditions in the usual way. The pattern is too stable, too law-like. It's as if nature is rolling dice, but rolling them with a very precise set of rules. So I tried to rescue the classical picture. I tried to say, maybe the electron really does go through 1 slit, but there's some disturbance, some field, some jitter that creates the pattern. And quantum mechanics says, okay, if that's your story, then measure which slit it goes through. Put a detector at the slits. Find out. So you do. And the interference pattern disappears. You get the simple sum again, like bullets. Now, if you're like me, you want to say, So the electron always went through 1 slit. The interference was just because we didn't know which one. But wait. Because here's the punch: when you measure which slit, you didn't merely learn something. You changed something. The very possibility of interference is tied up with whether the alternatives are distinguishable in principle. This is where I started to see the pattern. Quantum mechanics isn't telling you the electron is a wave or the electron is a particle. It's telling you, if you set up an experiment where the paths are indistinguishable, then you must add amplitudes, and amplitudes can cancel. If you set it up where the paths are distinguishable, then you add probabilities, and probabilities don't cancel. So what's an amplitude? It's not a probability. It's a complex number, an arrow, a little rotating thing that you add up, and then you square the length to get the probability. That sounds like mathematics, but it's actually a direct rule about nature. And it was the first hint to me that quantum probability might be real in a way classical probability never was. Now, the next thing my mind did, automatically, is what every decent mechanistic mind does. I started looking for the real event underneath the probability. I said, all right, maybe there's some hidden variable, some extra information that tells the electron which dot to make. Quantum mechanics just doesn't track it. This wasn't a crazy thought. Einstein had this instinct too. He wanted completeness. He didn't like the idea that the theory only gives odds. And a lot of people, very smart people, kept trying to put the gears back in. And here's where you have to be careful, because you can always invent hidden variables. You can always say, there's something we can't see. The question is, do they make new predictions? Can you test them? Otherwise, it's just story time. And I don't trust story time. I trust experiments. So suppose I try a hidden variable idea. The electron goes through one slit, but carries a phase tag or some internal compass that determines where it lands. But then I have to explain why measuring which slit destroys interference. The detector in that picture shouldn't change the electron's compass unless it disturbs it. So maybe you say, fine, the measurement disturbs it. But now you're stuck, because the interference disappears even when the measurement is so gentle that, classically, you'd think it shouldn't matter. Even more, it disappears when the information about the path exists in principle, even if no human looks. The whole system becomes entangled with the environment, and that forces a strange conclusion. It's not consciousness that matters. It's not observation as a mystical act. It's whether the alternatives remain capable of interfering. I'll tell you a thought experiment I used to imagine. Suppose the electron leaves a tiny mark, like a microscopic scratch, on the slit it passes through. Not enough to kick it much, but enough so that, in principle, you could later examine the slits and find which one was scratched. Then even if you never check the scratch, the interference is gone, because the two alternatives, left slit and right slit, have become different physical histories. So what then is probability doing? In classical physics, probability is about our knowledge of the system. In quantum mechanics, probability seems to be about the structure of the system itself, the way different possible histories can combine or fail to combine. The more I worked with quantum mechanics, the more I realized that this idea of histories wasn't just a metaphor. It was a calculational method that was unbelievably powerful, so powerful that I eventually built a whole formulation of quantum mechanics around it. Instead of asking, which path did it really take, I began to say, to predict what happens, I sum over all possible paths. Every possible way the electron could go from A to B contributes an amplitude, an arrow, and the final amplitude is the sum of all those arrows. Then the probability is the square of the result. Now you might be thinking, that's just math. It doesn't mean the electron really takes all paths. Good, be suspicious. I'm suspicious too. But notice what's happening. The theory works as if the electron doesn't have a single definite story between measurements. It works as if what happens is not a single trajectory, but a kind of weighted interference among possibilities. And that's exactly why the question, is the probability real, becomes sharp. Because the probability isn't slapped on at the end like a patch. The probability comes out of interference of amplitudes, which behave like physical things in the sense that they combine, cancel, and create observable patterns. For a long time I tried to hold two ideas at once. Nature is really deterministic underneath, and quantum mechanics is just incomplete. But then you look at the full structure, interference, entanglement, and the way amplitudes add, and you start to see that any deterministic completion has to pay a terrible price. I asked myself if this is true. Then what about two particles? What about correlations? If probability is just ignorance, then two separated particles should have outcomes determined locally by their own hidden information. That's the classical dream, no spooky coordination, no faster than light influences, just shared instructions. John Bell turned that tension into an inequality, a testable boundary line. And experiments, many of them, show nature violates the Bell inequality. So what do you learn from that? You learn that if you try to keep determinism by adding hidden variables, you can't keep locality in the simple classical sense. Or if you try to keep locality, you can't keep the classical kind of pre-existing values. You don't get to keep all your favorite classical comforts. That's the point. I stopped asking, is nature random or deterministic in the everyday sense? I began asking a different question. What does the theory actually say you can compute about nature? And what is the simplest consistent picture that reproduces those computations without pretending? And the simplest consistent picture, for me, was this: quantum mechanics doesn't describe a world of definite events with unknown details. It describes a world in which the basic predictive object is the probability amplitude, and the probabilities are what you get when you ask for definite outcomes. In other words, probability is not a measure of ignorance about an underlying fact. It's a measure of how the amplitudes line up or cancel given the experimental arrangement. This sounds abstract, so let me give you something concrete. Radioactive decay. Take a single unstable atom. You can wait, you can watch, you can know everything about its environment you like, and still, you cannot predict the exact moment it will decay. You can only say in the next minute, there's a certain probability. In the next hour, another probability. And it's not like classical unpredictability. It's not like, I don't know where the air molecules are. In the theory, the atom's survival is described by an amplitude that gradually shrinks in a very specific way. And when you finally detect the decay, you're sampling from that probability distribution. So again, chance appears not as ignorance, but as law. Even after all this, there's still a loophole people try to escape through. They say, okay, maybe quantum mechanics is probabilistic, but maybe the probability is just because we are limited. Maybe nature is still definite, but we can't access the variables. So I ask, what would it mean for probability to be real? In physics, real doesn't mean I can imagine it. It means it's part of the rule book you cannot remove without changing predictions. So let's look at what cannot be removed. You cannot remove the rule that amplitudes add when alternatives are indistinguishable. You cannot remove interference. You cannot remove the complex number nature of amplitudes. You cannot remove the fact that probabilities come from squaring the magnitude. So phases matter, cancellations matter. And you cannot remove entanglement correlations without breaking experiments. So the probability isn't sitting there as a placeholder waiting for a deeper deterministic variable. It is sewn into the structure of the theory. Now, I'm not claiming we've proven philosophically that the universe is fundamentally random. You can always write down some weird deterministic theory if you are willing to give up other things, like locality or simplicity. But physics is not a game of anything goes. Physics is the art of finding the simplest, tightest rules that match nature, and then respecting what those rules imply even when your instincts protest. People talk as if quantum mechanics is just statistics. But it's not like statistics in the usual sense. It's a machine for computing probabilities, where the intermediate bookkeeping is not probabilities at all, it's amplitudes. And that bookkeeping produces facts you can see: dark fringes, bright fringes, spectral lines, stability of matter, chemistry, lasers. So right before the revelation, I want you to hold one thought in your mind. When we say, the probability the electron lands here, that probability is not merely a confession that we don't know the electron's hidden address. It is the final shadow cast by a deeper object, the amplitude, that behaves like a wave of possibility, interfering with itself, and only turning into a definite event when you force nature to answer a yes or no question. I realized that the question, is probability real, is actually two questions disguised as one. Are the events random? Are the laws probabilistic? Quantum mechanics answers the laws are perfectly strict, deterministic in how amplitudes evolve. But the individual events you see are sampled according to probabilities derived from those amplitudes. So the randomness is not because the laws are sloppy. The randomness is because the laws connect the world to definite outcomes only through probabilities. I had been treating probability like a stain, like something that appears only when I don't know enough. But quantum mechanics was showing me a different kind of world, a world where certainty lives in the evolution of amplitudes, and randomness lives in the conversion from amplitudes to events. Think of it like this. In classical physics, the world is like a train on a track. If you know the engine's position and speed, you know where it will be later. Probability comes from not knowing the track conditions or the engine details. In quantum mechanics, it's more like music. The amplitude is like a complex harmony, phases like angles, waves adding and canceling. And when you finally listen, with a detector, you don't hear the harmony directly. You hear discrete notes clicks. The distribution of notes depends on the harmony. But the harmony is not a statement about ignorance. It's the thing you compute, the thing that interferes, the thing that predicts fringes. So is quantum probability real? Here's my answer. In my own plain way, quantum probability is as real as anything else in physics because it is not optional. It is not a patch. It is part of the basic rule for connecting the theory to observations. Now, does that mean the universe is random in some sloppy sense? No, the evolution is perfectly rule-governed. But the outcomes are not determined by hidden details that we have merely failed to uncover. At least not without paying a steep conceptual price. And when I finally accepted that, I felt something oddly relief, because I stopped trying to force nature into the shape of my childhood intuition. I stopped demanding a little classical movie behind the scenes. I allowed the actual structure, the interference of amplitudes, and the irreducible statistical nature of outcomes to be the picture. And the universe became stranger, but also cleaner, more honest. This changed how I see reality, because once you accept that probability is not merely ignorance, you begin to see a different kind of order in nature. An order that doesn't promise you a single inevitable future, but promises you something subtler, a precise structure of possibilities. And I think that's why quantum mechanics still makes people uneasy. We want the world to be a story already written. We want to imagine that if we had God's notebook, we'd see the exact landing point of every electron. But maybe that's not what the notebook looks like. Maybe the notebook is full of amplitudes, complex numbers, rules for interference, rules for correlation, rules for what can and cannot be made distinguishable. And the facts we experience are the samples drawn from that deeper structure. Now, I'm not saying you have to like it. I'm saying look at what nature does. Don't fool yourself. And if you feel a little uncomfortable, good. That discomfort is the feeling of your mind stretching to match reality. I hope you can see what I see. Not a universe that's broken because it uses probability, but a universe that's unbelievably rich because it lets possibilities interfere and then turns that interference into the solid world we touch. This is the beauty of physics, and I wanted you to experience it with me.